Welcome back. Let's continue our discussion of Chapter 20, a confidence interval for the mean. In the last video, we were using the sample standard deviation S to estimate sigma, the population standard deviation. And as we saw in the simulation, we need to use a different multiplier than the z-star critical value from the standard normal distribution. We end up using what's called a t-star critical value from the t-distribution. Now this was developed by a man by the name of Gosset. It's actually a very fascinating story. I would encourage you to read more about it. Gosset worked for Guinness Brewing, and because of the nature of his work, he often dealt with a small sample size. So he discovered that the normal distribution just didn't quite cut it for modeling the sampling distribution, and for that reason he developed the t-distribution. Gosset published under the pen name Student, and for that reason the t-distribution is often referred to as Student's t-distribution. The t-distribution is actually an entire family of distribution curves, similar to the normal distribution. We know the normal distribution is characterized by the mean and standard deviation, while the t-distribution is characterized by an integer called its degrees of freedom. And in this case, the degrees of freedom is simply the sample size n minus 1. So let's take a look at a few t-distribution curves. The curve denoted by the dashed red line is the standard normal curve. And then if you focus on the curve with the solid red line, this corresponds to a t-distribution with 4 degrees of freedom. So that would mean the sample size is 5. And what you notice is it resembles the normal curve, but the tails are a little bit fatter. See, the curve we're focusing on now is given by the solid red line. And then if we bump the degrees of freedom up to 9, that's the curve kind of trapped in the middle, notice the tail starts to kind of flatten out and get closer to the standard normal curve. Here's how you use a t-table to find the t-star critical values. So you start by going to the row of the table that corresponds to your degrees of freedom. In this example, I'm going to suppose the degrees of freedom is 9. And then you move over to the corresponding confidence level. If we're considering a 95% confidence level, we'd move to this entry here, and we see that the critical value is 2.262. So this would be the value for which the area under the curve to its right is 0.025. See, between the two tails, we must have an area of 0.05. This is a 95% confidence level, so the area under the curve to the right should be 0.025. As I pointed out earlier, as the degrees of freedom gets bigger, the tails of the t-distribution curve start to flatten out and more closely resemble the standard normal curve. So if you were to go to the last row of the t-table, which might list the degrees of freedom as infinity, that actually corresponds to the standard normal curve, and the value you get from the table would simply be the z-star value that we were using before. We do have a few assumptions to check before using the t-model. The first is the independence assumption, and for this we check the randomization condition. We need a sample that is a simple random sample. The other assumption is called the normal population assumption, and for this we need to check the nearly normal condition, which says the data come from a distribution that is unimodal and symmetric. So here's how we check this condition. We make a histogram. If the sample appears to be roughly normal, then you can assume that the population follows a normal distribution. Let's summarize how to construct a confidence interval for the mean. And this is also called a one sample t interval for the mean. We take our sample mean, y bar, add and subtract this critical value t star, which you could include this n-1 subscript to denote the degrees of freedom. So this value is found from the t-table, as I demonstrated earlier, and you multiply by the standard error of y bar, which is the sample standard deviation s over the square root of n. That's all for now. See you next time.